invitation is at 6:30. Can you please check it? Is at 6:30. They
Let
are
it
going
be,
to give
let
us
it
some
be.
instructions.
Not a problem. Regular session will start at 7. We will join opposed to Ashish Sir's class.
No. The invitation for that meeting itself is at 6:30. That is Arunachalam sir.
No, I think you can tell them that, there is a class which goes at
Yes,
7.
sir, I will do it, sir. Not a problem. I will do it, code
I
office
mean,
and
code office themselves have not informed me that, I should not be taking class. I don't know how they can arrange this meeting.
tomorrow, sir, tomorrow morning I will confirm.
Yeah,
Not a
tomorrow
problem,
we'll have the, review session. Okay.
sir.
Okay,
Sure.
sir. Thank you.
Thank you, sir.
So my screen is visible to you.
Right, sir. It's visible.
Sir, visible, sir.
Okay, so I will just recap quickly before we proceed further. We were talking about laws of thermocouple circuits when we stopped. We talked about law of homogeneous material, where we said that for a thermocouple to work, you need at least two junctions formed by two dissimilar metals. Like you will have metal A and metal B, and you will form two junctions, junction 1 and junction 2, which are maintained at two different temperatures, T1 and T2. Then we said that the output, typically, as I said, the P-type wire is cut open, and where you can actually measure the output. And the output only depends on the junction temperature, J1 and J2, okay, T1 and T2. And it is independent of the temperature elsewhere in the circuit. Then we talked about law of intermediate material, where we said that if you have a thermocouple circuit, which is made out of material A and material B, and you have junctions J1 and J2. And if you, let's say, cut the material A and introduce a third material, material C, then the output is not going to be affected by the insertion of a third metal into one of the legs. And we said that it is not only in one of the legs, but if you also, open one of the junctions, let's say here it was the junction 1, J1, and you introduce a third material at the junction, as long as these two separate junctions which are formed now through the material are at the same temperature, T1, like here the temperature was T1, and you have brought in the third material, that is material C. But in doing so, the one junction here becomes two different junctions, but these two junctions are now maintained at the same temperature, the original junction, that is at T1. So if you do that, then the output is not going to change through the insertion of this third material. We talked about law of successive temperature or materials. First, we talked about law of successive temperature. So here we said that if you have two different materials, material A and material B, and you have junction temperature T1 and T3, whatever output you get will be sum of the two different thermocouple circuit. In one case, you have material and material B, but the temperatures are T1 and T2. Plus, in the second circuit, the temperature is T2 and T3. So the combination, the addition of the outputs from these two circuits will be same as if the junctions are maintained at temperature T1 and T3. This is called law of successive temperature. And then we also talked about law of...
Sir?
Yes.
Sir, one doubt, sir. This for
law of successive temperature, in this case, sir, T2 has to be in between T1 and T3, right? Sir? If I'm understanding right.
Yes. It has to be between T1 and T3. It has to be an intermediate temperature. And,
Thank you, sir.
yeah. Similarly, here you talk about the law of successive material, where you talk about material A and material B. And in this case, the junction temperatures are not changing. But if you have material A and material B, whatever output that you get will be sum of these two circuits, where you have material A and material C, and then you have material C and material B. Okay, and this is known as the law of successive material. So I wanted to show you the typical thermocouple temperature table, and show you one small example where we need to read the values from this table. So typically in a thermocouple temperature table looks like this. The reference temperature is usually the ice point temperature, that is 0 degrees centigrade. And in the temperature thermocouple table, we'll mention what type of thermocouple that we are talking about. For example, this particular one talks about K-type thermocouple. And different rows would indicate temperatures in degrees centigrade. Okay, so 0, 10, 20, 30, 40, and so on, degrees centigrade. And then you have different columns here. Okay, and then the entries in each one of these rows and columns indicates. Okay, so for example, so these numbers here indicate the second digit of the temperature. Like for example, if I have 15 degrees centigrade, I go here 10 and I go 5 here, right? 15. So this 0.597 is the output corresponding to 25 degrees centigrade as the hot, 15 degrees centigrade as the hot junction temperature, and the reference junction is at 0 degrees centigrade. So this will be the corresponding output. And let's say my temperature is 100 and let's say 95 degrees centigrade. Then I go 90 here and 5 here. So I get 95 degrees centigrade here. Okay. So this is how, so 3.889 will be the Seebeck output voltage of a thermocouple circuit comprising a K-type thermocouple with the hot junction at 95 degrees centigrade and cold junction at 0 degrees centigrade. Right. So after knowing this, let us work on this simple problem, which says that we have a K-type thermocouple, and this thermocouple circuit operating with a reference temperature of 25 degrees centigrade. Okay, so that means the cold junction, you have just put it in the room and it is exposed to ambient, which is at 25 degrees centigrade, not at ice point temperature. So this K-type thermocouple circuit operating with a reference temperature of 25 degrees centigrade shows an output voltage of 2.4 millivolt. Okay, so when you put in the your voltmeter, you read an output of 2.4 millivolt. The question is, predict the temperature of the hot junction or the source temperature from this measurement. So how do you do that? So you go to the K-type thermocouple, because we are using K-type thermocouple. So this is the K-type thermocouple table. Now this table is prepared with the reference temperature at ice point. Okay, but in your experiment, your reference temperature is 25 degrees centigrade. So what you do is you use the law of successive temperature. That means in your thermocouple table, your hot junction temperature is something that you want to measure. And the cold junction is at ice point. So this is the thermocouple table. Okay. But in your case, your hot junction is something that you want to measure. And the cold junction is at 25 degrees centigrade. Okay, not at 0 degrees centigrade. So this is the circuit that you actually have. And this is the one that is showing you in the table. Your table is really made of with the T3 as 0 degrees centigrade. So how do you approach? So you say that my temperature, my output, when my temperature is at hot junction temperature, and my cold junction is at ice point, will be equal to the hot junction temperature, and the cold junction it has 25 degrees centigrade. Then the next circuit where the hot junction is at 25 degrees centigrade and the cold junction is at 0 degrees centigrade, right? So you can use law of successive temperature. So what you really do is that first you need to read the output when the thermocouple operates with this temperature limit. So you have 25 degrees centigrade and 0 degrees centigrade. So you go to the table and you see that already, this is at ice point. So you have to really read what is the output voltage corresponding to 25 degrees centigrade at the hot junction. So you read this as 1 millivolt. Okay. Then this is the output that you get in your experiment where the hot junction is at some unknown temperature and the cold junction is at 25 degrees centigrade. So this output is recorded as 2.4 millivolt. Okay. Now you basically add this 2.4 millivolt plus 1 millivolt, that is 3.4 millivolt. That is the output of this circuit. Okay. So when you know the output and you know the cold junction, you can definitely find out the hot junction temperature. So basically for an output voltage of 2.4 millivolt, the total voltage would be 3.4 millivolt, right? For the junction when the cold junction is at ice point. Now you go to the table and corresponding to 3.4 millivolt, you find what should be the temperature. So you look at the entries and you can see that, this 3.4 is between this and this, okay, between basically 3 and 4. And so you read that the temperature is somewhere between 83 degrees centigrade to 84 degrees centigrade. So you approximate that it is around 83 point something is the temperature. Okay. So that is how by doing experiments, when the cold junction is not at the ice point temperature, you can use the thermocouple tables, which are typically prepared at ice point temperature to predict your hot junction temperature. But if you do experiment when the reference junction is at 0 degrees centigrade, and if you just measure the output from your voltmeter, you can directly read the temperature. You can directly go to the table and read the temperature, and you can sort of estimate that way using the table. Right. So there are a few other aspects regarding thermocouple I would like to talk about. What is important is when you prepare the thermocouple that the two different wires, one positive and one negative, they need to be in contact only at the tip, not anywhere else. Okay. So to ensure that, typically these wires are, sheathed with some kind of covering. And these are different materials which are used as insulation materials, nylon, PVC, enamel, and so on. And depending on the temperature range that the thermocouple works in, the different insulation materials are used. So this is typically how a thermocouple looks like. It is basically insulated all around, and the wires are connected only at the tip. Okay. So what are the different junctions that are made out of thermocouple materials? Typically, the junctions are formed by twisting the tips of the two wires together. And either you do welding or you do soldering to make them in thermal contact so that there is no air gap, because even if you twist, there is always going to be an air gap between the metals. So in order to have a perfect thermal contact, you typically solder it, right? And or weld it or braze it. So this is how it is typically done. You sort of twist the wire and you weld it. You can do this twisted weld junction, or you can do the butt welded junction, where the wires are not twisted but just brought side by side, facing each other, and then you create a weld. The different types of junctions are shown here. First one is the grounded junction. So here, the positive and negative wires are not directly, twisted with each other or welded. There is a metal sheath here, and these positive and negative terminals make electrical and thermal contact through this metal sheath. Okay. And this is used when, let's say, you do not want the thermocouple to be in direct contact with the process fluid, whose temperature you want to measure. Let's say you don't want to directly expose, let's say the fluid is corrosive and it will affect the lifetime of the thermocouple. So instead of directly, connecting at a point like this or like this, you just use this metal sheath, which is resistant to the fluid, and you make thermal contact this way. Then you can have an exposed junction, and this is typically, done. I mean, as it is shown here, they are basically physically making contact, and you make a weld or solder joint here, and then the ceramic sheath, which is basically used to support, provide structural rigidity to these thermocouple wires where you are basically installing. Then you have a separated wire junction. This is again, the ceramic sheath used for structural rigidity, and the P and N type wires here are not physically in contact, neither by forming a bid or nor through a metal sheath. They are just hanging in the fluid. So here, in order to maintain electrical contact, it is essential that the process fluid itself be conductive in nature. So these P and N type materials, they actually make thermal contact through the fluid itself. And then you have button junction, where it is similar to the metal sheath here. The difference is that here it is a complete like a tubing arrangement. In another case, you can just have a flat surface here at the end, where the P and N type can come and make electrical and thermal contact. And the whole thing is, again, is encapsulated in a ceramic sheath.
Sir, in that grounded junction example, how does that response time increase?
So the response time would, increase because typically, if you have a, small bead here, and as the process temperature change, you know that when we talked about the transient response of a thermocouple, we talked about the mass times specific heat, MC, right? The time constant is inversely related to the mass times the specific heat. That means the bulkier the system, then it will take a long time for the system to equilibrate with the thermocouple to equilibrate with the surrounding. So here, since you are using a metal sheath, of course, you are increasing the mass of the system. And therefore, typically these grounded junctions will have a much more slower response as compared to the welded junctions.
Got it, sir. Basically, it is increasing some
It
resistance
is
there.
increasing, yeah, it is increasing the thermal resistance.
Yeah.
So
Okay.
it will be slow, yeah, in terms of response.
Got it, sir.
But good thing is that, I mean, there are some corrosive fluid which will, degrade the wires. For long-term use, you have a metal sheath which is, resistant to the process plate. You compromise in terms of, the dynamic temperature measurement, but, that is something that your system requires. So you can make a connection through a metal sheath. Right, so we talked about differential thermocouple. So in situations where you want to measure temperature difference between 2 points, one approach is to measure the temperatures of these 2 points, and then you subtract them and you get what is the temperature difference. But this will basically lead to error propagation, as you have studied in when we talked about uncertainty. So in order to avoid that, one approach is to use differential thermocouple. And you can use differential thermocouple with a low noise, high gain amplifier. Because typically, the difference may not be very large, but if you have the appropriate circuit, you can actually bring it to a detectable limit with a reasonably low uncertainty. So this is how the differential thermocouple look like. Here you can see that there is no hole junction as such, right? We talked about in the last class that can we measure temperature without using a hole junction. So you cannot measure temperature, absolute temperature, but you can measure the temperature difference. Okay, so here, so you have basically 2 junctions, T1 and T2. You want to measure the temperature difference between these 2 points. So what you do is you have the P-type wire running from the tip to the voltmeter. Okay, so this is basically the P-type wire, and you cut open and you insert a voltmeter here just to measure the output. And you can see that the N-type wire runs through these 2 terminals. Okay, so you have N-type here going all the way to the other point. Now, you could have just measured using, N and P type thermocouples, the temperature at this point with a cold junction. And you could have measured the temperature also at this point with a cold junction. But here you have now completely, gotten rid of the cold junction. Instead, you join the 2 points with an N-type, and the P-type basically connects to a voltmeter. So this is known as differential thermocouple. And many times this is used for calibration purpose, because you know that if 2 different points at the same temperature, they should be reading 0 temperature difference. So if you just put in there, you can, let's say you say that, okay, I have one of these thermocouple is something that I have purchased from a very reliable company. And this thermocouple, let's say I made it, buying individual wires. And this is something that the company has tested and verified, and I want to really verify the thermocouple here. So you have two sources whose temperatures that are the same, and you stick in these thermocouples to these two places, and you know that the voltage difference should reach 0. And if the voltage difference is not 0, then there is something wrong with the thermocouple that you are testing. So this is used to basically calibrate thermocouple as well. Now, if you want to amplify the temperature difference between 2 points, and sometimes the temperature difference may not be very large, and your uncertainty of measurement is affecting the reliability of your data, then you can have these kind of junctions in series. Okay, so you can have a series of these junctions in the form of what is called thermopile. So thermopile is basically an array of thermocouples where the output basically increases as you add on the number of thermocouples in the thermopile. So here you can see that this is the point, the lower temperature point, and this is the high temperature point that you want to measure. Let's say this is your ambient temperature, and this is the temperature of some object that you want to measure. So instead of having only two terminals, T1 and T2, something like this and that, you basically have a series of hot and cold junctions. Okay, so when you do that, the output from each times the number of elements in the array will give you the total output. Okay, so instead of one output, now you have n times. So what this voltmeter reads is n times that value, and so you are basically amplifying the output particularly when the temperature difference is very low. Then you can also use, so here you have used thermocouples in series, but you can also use thermocouples in parallel, particularly when you want to measure average temperature of a region. Let's say you have a metal plate and you want to know what is the average temperature of this surface. One approach is to keep measuring temperatures at different points, okay, and that may take more time, but you can use in one single circuit. You can have multiple junctions where each of these points will refer to the different points on the surface on the plate, which average temperature you want to measure. And here you can see that all the N-type wires are connected to one terminal. Okay, so you can see that this is the N-type here, this is the N-type here, this is the N-type here. They're all connected to one single wire, and this is the one terminal basically around the output voltage, and all the P-type wires then also connected as one terminal. Okay, so in this way, the output voltage basically is representative of the average temperature of the surface. Okay, so this is how thermocouples can be used in parallel to measure average temperature of an object or surface or any fluid or anything. But there is one problem. The problem is that the temperature measurement is highly sensitive to the lengths of the wire being unequal. If the lengths of the wire are unequal, then the resistance will be different, and the current would find different paths. So this will bring inaccuracy into the system. So one way to equalize the length of the wire or the resistances along the wire across the output voltage is to introduce what is called swamp resistor. So the swamp resistor basically is introduced to make sure that for each one of these terminals, the junctions, the length that it takes from the voltmeter to the junction on the positive side and that on the negative side are equal. Okay. So if that is done, then you can actually rely on this circuit because it will have equal resistance on both the limbs, which is required for accurate temperature measurement. Right. So this basically,
Sir,
yeah.
Can we go to the sir? This slide, sir, these three terminals we are measuring the temperatures, no, sir. So three individual terminals will generate some voltage. So that voltage will not increase, sir.
No, that's what I'm saying, that this output voltage is a consequence of the average effect of these terminals.
So it will not be the sum of it, it will be the consequence of it.
Yeah, it will be the consequence of the average of these circuits.
Okay.
It will not be
Okay.
just sum.
Okay, sir. Got it, sir. Thank you.
Okay, so I mean, this gives you some basic understanding of how thermocouples work, what are they made of, and how you can use different arrangements to measure temperature. And it particularly talks about the physics behind the thermocouple, the Seebeck effect, Peltier effect, and the Thomson effect. So with that understanding, now let us talk about few scenarios where we may encounter some kind of errors when you try to measure temperature using thermocouple and how to resolve them. Okay. So we talk about the errors in temperature measurement in the context of measurement of temperature at a surface when you try to measure the temperature of a surface, or temperature inside a solid that you are interested to measure, or you are interested to measure temperature of a flowing fluid. So in three different scenarios, three different examples, we will try to estimate the errors that are possible because while doing temperature measurement using the thermocouple, and how do we correct for the error. This is the objective. Now, first, let us talk about what are the possible sources of error when you actually measure temperature of a surface. So let's say you are trying to measure temperature of this surface, okay, which is at temperature Ts. So you basically bring in the thermocouple here. So it has two wires which are making contact here, electrical contact. And the other end of these two wires is in a reference junction, and you have some voltmeter to measure. You can estimate the temperature using the temperature table. Now, these thermocouple wires are metal wires, and metals are good conductor of heat. So when you put in the tip here, what happens is some of the heat from this surface starts getting conducted through this thermocouple wire. Okay. So essentially, there is some heat leakage that happens from the surface, whose temperature that you want to measure, into the thermocouple wire. So essentially, I mean, this problem is called lead wire conduction error. Okay, so essentially, the temperature that you end up measuring is going to be lower than the actual temperature of the surface. If the actual temperature of the surface is Ts, your thermocouple tip is going to measure a temperature Tt, which is going to be lesser than Ts. Okay, because some of the heat is already drawn along the wire and it is basically lost to ambient. Okay, so this introduces error, okay, while measuring temperature of surface. And as you know, thermocouple is a measurement of temperature using thermocouple is an intrusive method. You basically not only measure the quantity that you want to measure, you are also perturbing the original system, right? Because you are taking away some of the heat in the thermocouple. Whereas if you use an IR camera, infrared camera, that will be a non-contact, non-intrusive method, right? Because you will not really interfere with the surface, and it just work based on the principle of electromagnetic radiation, which we'll talk about briefly towards the end. So it says that if the ambient is less than the surface temperature, then the temperature that you measure is basically less than the surface temperature. And this is attributed to the fact, as I said, the lead wires will conduct heat away. And when the lead wires conduct, the heat is transferred to the surface for compensation, and that basically introduces error. So the surface temperature junction is less than the surface temperature elsewhere. Okay. And this basically leads to measurement error. Now, how do we compensate for this conduction error in applications where the temperature you are taking some decision, or the instrument itself is taking some critical decision based on the temperature that is measured using the thermocouple, then the accuracy of measurement becomes very important. So one of the ways that you can compensate for this heat loss is by including these heaters all around the thermocouple wire. Okay. So what happens is, if you know the conductivity and the material property, the geometry of these wires, you can very well, and what the surface condition would be, you can very well estimate what would be the conduction heat loss in terms of this Q2, which is going along the wire. So you have some heating arrangement around the thermocouple tip, which basically compensates for this Q2 that is leaving because of conduction. This heater supplies that amount of heat towards the tip. Essentially, whatever heat was getting lost, the same amount of heat is coming from the heater to the tip. So essentially now, whatever temperature that you will measure will be same as the actual temperature of the surface. So this is basically summarized here. Your Q1 is the total amount of heat that can come into this point. And Q1 minus Q2 will be the Q3, which is going as some radiation loss from the surface. So you basically can neglect the effect of this heat loss here on the surface temperature. So here you can see this is called a compensated probe. So typically, if you do not have any kind of compensation, as the surface temperature increases, as you know that the heat loss is going to be a function of the temperature difference between the surface temperature and ambient temperature. So as you have more and more temperature of the surface, this error that you encounter, that is the temperature that you measure minus the actual surface temperature, is going to increase. Okay, so because you are going to have a higher and higher heat loss, so this temperature is going to increase. Now, if you include this kind of heating arrangement to compensate for the loss, then your TT minus TS is going to be 0. Okay, that means the temperature that you measure and the actual temperature of the surface will be the same. And this is known as the compensated probe arrangement in thermocouple.
Sir, I have a question over there.
Yeah.
So basically, suppose at time t is equal to 0, the thermocouple is in contact with surface.
Yeah.
Okay. So suppose at t is equal to delta t, like after some time, wouldn't be the thermocouple will become hotter compared to the t is equal to 0 instant? So my point is that if the time progresses, the thermocouple temperature will also increase, and at a particular after a particular time, the thermocouple should be in thermal equilibrium with the surface.
No,
So
no.
if I measure,
See what is happening, I will tell you.
Right.
See, typically your surface temperature is at a higher temperature than ambient. Okay, we are talking about that case. So
All right, sir.
let's say you have somehow managed to insulate the surface elsewhere, except the point where you want to measure the temperature, this tip. Now, the surface temperature is higher than the ambient temperature. That means higher than the thermocouple temperature. So, when there is a temperature difference, heat will try to flow into the wire. And these are metal wires, so they are highly thermally conductive. So, heat will conduct. Now, where that heat will go? The heat will go along the wire close to the surface, but then away from the wire, heat will go to the surrounding. Because the surface area is increasing as you go along the wire. So heat goes from the surface into the wire and from the wire into the ambient. Whatever insulation you try, but eventually the temperature is going to go to the ambient. So since this is going to be the heat flow path, heat comes here and goes into the ambient. So always the tip temperature here is going to be lower than the surface temperature. You are right that this is going to be heated up, but when this heated up, what will happen to the heat transfer? There is going to be higher heat transfer from the wire to the ambient. So this heat path will always be there, goes from the surface into the wire and finally to the ambient. Okay.
And that loss will be linear, sir, right? If I'm not wrong,
That
because
loss, yeah, that loss, I mean, as you have I mean, if the surface temperature increases more and more, that loss is going to increase more and more. That is indicated by here, right? So 0, as the surface temperature increases, let's say for some application, you are controlling the heat input and the surface temperature initially 50 degree, you are trying to measure, then 60 degrees, 70, 80. Then you will encounter more and more error as the temperature of the surface is higher and higher. Okay.
Thank you, sir. I got it.
Now, we talk about we try to predict what is the conduction error, what is the consequence of this heat loss into the wire and how much error can we expect. So we talk about a lead wire model. Okay. And so we do some heat transfer analysis to actually predict the error. So typically, if you cut a thermocouple wire, this is how you see. Okay. So you have the wire 1 and wire 2. These are basically circular wires. One is N type, one is P type. And these are encapsulated in this plastic. So this is basically a insulating material. And these are wires. So you cut the thermocouple wire. This is what you are going to see. So let's say you have wire 1 is having a radius of RW1 and thermal conductivity of K1. And the second wire is having a radius of RW2 and thermal conductivity of K2. And this is, the outside, it is sort of a capsule shape. Okay. And let's say the width in this direction is L1 and width in this direction is L2. Since this kind of geometry is complicated, we cannot do a simple heat transfer analysis of this kind of geometry. We create a thermal equivalent of this thermocouple. Okay. So where these two wires, the effect of the heat loss through these wires is brought into a single equivalent wire, which is having a radius of R1. From RW1, RW2, the combined effect of that in terms of heat loss is dumped into R1. And this insulation is basically brought by saying that we have another, concentric insulator of radius R2. Okay. So this situation is, we have simple formula to actually do a heat transfer analysis, this kind of cylindrical arrangement. But this kind of complicated geometry with a flat top and bottom and curved sides, we cannot do a heat transfer analysis. So you build a thermal equivalent of this system. So when you do a thermal equivalent, there are certain things you have to preserve. Okay, so we talk about what are the things that we preserve in the next slide. But before that, this is what I wanted to talk about. So heat flow comes from the surface along the wire, but finally it leaks in this direction and finally comes to the ambient. Okay, so this is the typical path. It goes along the wire. From the wire, it comes to the insulation, and from the insulation, it goes into the ambient. Okay, so this is the typical heat flow path. So how do you build the equivalent? There are certain things that you want to preserve. That is, when you do a thermal equivalent, the area thermal conductivity product should be same for the two wires and the single wire. That means you have the thermal conductivity into area in the two-wire arrangement should be equal to the thermal conductivity of the one-wire arrangement. So one-wire arrangement is the new wire arrangement. This arrangement here, this is called one-wire. This is the two-wire. And this should be equal to K1 into AW1. That is thermal conductivity of here wire 1, K1 into the area of cross section of this, plus K2 into area of cross section of the second wire. This is the first thing that we need to make sure when you build a one-wire equivalent. All these two-wire thermal conductivity area need to add up to bring it to the equivalent one-wire model. Second thing is that the area of cross section, let's say if you say that these two wires are of same area of cross section, this is RW1 and RW2 basically are the same. Okay, so here if AW1 and AW2 are basically same, then you can write this as K1 plus K2 into AW. So that means the K times A in the equivalent model is going to be K1 plus K2 into AW. Then the insulation layer is basically replaced by a coaxial cylinder of inner radius R1 and outer radius R2. And this is something we have shown it here. So your R2, the outer radius here will be basically L1 plus L2 divided by 4. Okay, so this is basically the equivalent, thermal equivalent of the outer radius. Since thermal conductivity of insulation layer is small compared to the wire, because the wire is made out of metal, the insulation material is made out of plastic or polymer. So it is considered that heat conduction in the wire is axial and in the insulation layer it is radial. So that is what we talked about, because these wires are basically insulators. So there is negligible heat transfer in this direction compared to in the insulation layer compared to the heat conduction through the wire. But this heat cannot continue to go infinitely in the wire. With ambient is at lower temperature, the heat has to go radial direction through the insulation layer into the ambient. So it is important to note that the heat conduction in the wire is axial and in the insulation layer it is radial. So this is basically the equivalent model that we talked about. So the heat conduction comes into the thermocouple wire and then it goes by conduction from the metal wire to the polymer or plastic covering the sheet, and from the plastic sheet it finally goes to the ambient through convection. Okay. So there is conduction along the wire, then conduction from the wire through the polymer layer, encapsulation layer, and from the wire surface plastic surface, it goes into the ambient through convection. So if you build a resistance equivalent, so you have temperature of the wire somewhere here. Then this is the resistance of the insulation layer. Basically, this thickness gives you the resistance. Ti is the temperature of the surface here of the plastic. And Ta is the ambient temperature. Okay, so this is another resistance at the interface of the plastic encapsulation and the ambient air. This is basically RF. Okay, and the resistance from the surface of the metal wire to this, because of this polymer thickness, brings in the insulation layer thickness, Ri. So from heat transfer, you know that the resistance of a concentric cylinder having radius R1 and radius R2 is basically 1 over 2 pi into K insulation layer into ln R2 by R1. So this is known for heat transfer. Similarly, the resistance, convection resistance at the surface will be 1 over A into H. So that is 1 over 2 pi R2. Okay, let's say the unit length. So 2 pi R2 into the heat transfer coefficient H. So these are basically the resistances. And knowing the resistances, we can now do we can develop a model to actually understand how much error we would encounter. So I will stop here, but we'll continue in the next class. Yes. If you have any question, then we can discuss.
Professor, sir.
Recording stopped.
Yeah.
Sir, just I want to pass one message to my batchmate, if you allow me, sir.
Yes, yes, please do.
Friends, the code office has told me that whatever the mock exam tomorrow they plan, it will be available in 2nd and 3rd. So those who are missed tomorrow may join on 2nd also, in 3rd also at the same time. Okay, thank you.
Okay,
Thank you,
sir,
sir. Thank you.
Arunachalam, sir. But what will be syllabus, sir, Arunachalam, sir? Like what should we study for that exam?
Nothing, yeah. We will discuss later.
Okay, Arunachalam. Thank you.
Thank you.
Okay, so tomorrow we will have the summary of what
Yes.
all we have covered. I mean, and what will be asked in the midterm exam. I will tell you I have already told you that I will not be asking temperature measurement, and so I will only limit it to the order subsystems. Okay, but we will
Up
have
to 14th, up to 14th class, sir.
Yeah, whatever, whichever class, we covered the order subsystems, till that we will be asking. So we'll have
Sure,
a
sir.
quick recap tomorrow. Okay,
Right, sir.
about that. Then we will have the exam.
Okay, sir.
Thank you so much, sir.
Okay.
Thank you, sir.
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 Thank you, sir. Thank you.